So good morning and welcome back. So today we'll come to the last section of the present chapter, and actually that will be the end of the last purely mathematical chapter, and then from next Tuesday onwards we'll look at physics applications in various fields. And so today we consider curvature and torsion. So that's 5.7. So in differential geometry, if you look at covariant derivatives on the tangent bundle or on the frame bundle, curvature and torsion are usually mentioned together as properties of a covariant derivative. And so there might be the impression that one might get the impression that the curvature, which we defined quite generally on the principal bundle, that there will also be a torsion, which is quite generally defined on the principal bundle. On a principal bundle, if there is a connection 1 form defined, but that is absolutely not the case. So a torsion requires additional structure beyond the structure you have on a principal bundle that's equipped with a connection. Now, in the context where curvature and torsion are usually mentioned together, so that's the covariant derivative of an affine covariant derivative, there the frame bundle, which is the natural principal bundle in that setting, carries a canonical structure which allows you to define torsion. So sometimes it seems like there is no extra structure required, but in more general cases it is. So so if I say curvature and torsion here, I mean on a principal bundle and torsion with an extra structure. So the key technical definition we have here is that of a covariant exterior derivative. The definition, if we start with a principal G bundle, P over a base space M with a group G acting from the right, be a principal bundle, and we consider also a K-form. Let phi be a K-form. Well, an arbitrarily valued, so a flower-valued K-form. And so this has to do with the remark I made last time that if we talk about a Lie algebra valued K-form or a vector space valued K-form or a whatever valued K-form, we should make sure that the thing still deserves the name K-form for all the operations we perform on it. And so I make this explicit here. So let phi be a whatever valued K-form. Then this object capital D acting on phi is again is a K plus 1 form. So it actually takes K vectors here on the principal bundle, and it maps to, well, whatever it is. It maps to the flower space, and it's defined particularly simply as d phi as a K plus 1 form. It eats K vectors, so x1, or vector fields in this case, up to xk, and this is simply defined as the ordinary exterior derivative whose definition doesn't depend at all on where these, what the space flower is, and the connection, I forgot the connection, a principal bundle with a connection 1 form. That's important. With a connection, well, I just write connection, but I mean connection 1 form omega that lives on this principal bundle. Then I plug in all the x's here, but only their horizontal parts. So this is the horizontal part of x1 up to the horizontal part of xk plus 1. Here must say k plus 1, k plus 1. And that's it. And of course, you remember that in the definition of this horizontal projection, the one form or the connection make their appearance. All right? So that is the covariant bit of the covariant derivative. So then this guy, this map is called the covariant exterior derivative. So the covariant being the qualifier, covariant exterior derivative, well, of the K-form phi. Okay, so this is an incredibly useful definition, and of course, for actual calculations, we'll figure out how to represent this horizontal projection by some more explicit expression. Now, the key notion of curvature is defined as follows. So again, we have a principal bundle on which there sits a connection one form. Then the curvature of the connection, so that's the property of the connection. And if I say connection, technically, of course, this is equivalent to having a connection one form. So the curvature of the connection one form is the Lie algebra valued two form that goes by the name capital omega. Well, it eats two vectors on the principal bundle. So it's a two form on P. Now we're firmly on the principal bundle. And it's Lie algebra valued. That means the Lie algebra of the group G that belongs to this principal G bundle here. And it's simply defined as omega is the exterior covariant derivative of the connection one form. You see, the connection one form is Lie algebra valued. So in this case, flower is the Lie algebra. So this is also Lie algebra valued. Okay. But I used here flower, not the Lie algebra, because we will use this covariant exterior derivative also for objects that are not Lie algebra valued. Okay. So therefore, this generality at that point. Now, of course, this is just the d omega of Hor x1, Hor x2, but we want to make this more explicit, so claim. If you write down this omega, it can actually be, so the Hors can be replaced by writing the exterior derivative of the connection one form. And then you have an extra term, and this extra term is often written omega wedge omega, but this is misleadingly simple. One should probably write a double wedge here, and you'll see in a second why double wedge. Okay, so what do I mean by this double wedge? Well, I need to define this because you see this is Lie algebra valued and this is Lie algebra valued, and if you think of the definition of the wedge, and you have two one forms, then the wedge should actually yield 0. That's right, huh? So that sounds very strange. So it cannot be the normal wedge, but then these are not function-valued one forms, so function-valued covector fields, or in other words, covector fields, but the values are in the Lie algebra. And now we already start feeling, okay, and that doesn't commute. The functions commute, the Lie algebra doesn't commute. And so, make a long story short, it's a different type of wedge here because these guys are flower valued, Lie algebra valued. And we declare this by providing two vector fields on P. So these are both vector fields on the principal bundle, and this is simply omega of x, omega of y. What is omega of x is a Lie algebra element. That's a Lie algebra element. And the only way I can marry them is to use the Lie algebra bracket. So that's the bracket that lives here on this Lie algebra that we induced there from the differential geometric Lie bracket on the whole group by virtue of the left invariant vector fields, right? And so the whole thing is, again, Lie algebra valued, as it should be once you plug into vectors, but before you plug them in, it looks like this. Okay? That's it. Okay, but again, in the literature, very often there is just a wedge, and that easily leads to confusion, okay? Because the wedge doesn't easily extend to any flower space. And if the flower space, as in this case, is the Lie algebra, then we define it like this. We later have opportunity to define the wedge between a Lie algebra valued one form, two form, and so on, and a only vector space valued form. How does that work? Well, that can work. Then it's the application of this and this, but then the vector space must be a representation space for the Lie algebra. So then we will have again another wedge, which again in the literature is often written just as the wedge. So we have to distinguish them, and once we properly distinguish them, we can of course drop the explicit distinction, but there is a distinction. Okay, so we have this, this thing, and it's probably worth proving this. Is there a question so far? Okay. Well, maybe one remark I could make here. Namely, if the Lie algebra is a matrix group, and the group is a matrix group, and hence the Lie algebra is represented by matrices of the same size, then we can, of course, write the Lie algebra valued character here by providing indices ij, because these are the indices of the Lie algebra row and column. Okay? And then this becomes just the exterior derivative of the ijth component of this omega. But remember, the d has nothing to do with acting on these on these indices, because these are Lie algebra indices. Every omega ij for fixed ij is a one form where on the principal bundle, not on the base space, on the principal bundle, and on this acts the exterior derivative. So these are equations for every ij. And then this extra term back here, this can be written explicitly even without providing the xy. If we if we use omega I k wedge omega k j, so then there's just this sum here. Okay. So this is only for matrix groups, because in matrix groups, of course, this Lie bracket is given by the commutator. So it's really first one and then the other, and then the wedge also commutes the two. So there the wedge is justified, and these are two one forms for each combination. It's the sum of these. So maybe this also gives some clarity, but this only works for matrix groups. If you have a general Lie algebra where the Lie bracket is not the commutator in any sense, because you don't have a natural multiplication between the two, which generally is the case, then you have to write it this way. Okay, this is already a special case down here. And but now let's try to prove this this thing here. So, proof. In order to prove this, we know that omega is a two-form. We can, of course, use the fact that omega is bilinear. Is C infinity bilinear on P. C infinity P bilinear, and hence we did this trick before. We can, of course, decompose any of the vectors that xy that appear in the slots of omega into a vertical and a horizontal part and discuss the cases independently. So we have three cases. We have to first consider the case that both the vector x and the vector y that we plug into the omega, so vectors on TP, vector fields on TP, are vertical vector fields. Okay? So if they're vertical, then there exist Lie algebra elements A and B, such that X is the induced vector field, the vector field induced by A, and Y is the vector field induced by B, two vertical vector fields. And now we simply prove this claim by evaluating the left-hand side and the right-hand side separately. So the left-hand side of the equation is then, if you plug in the vectors xy, well, it's just xa, xb. And this is defined as, by the definition of omega, this is the covariant exterior derivative of the connection 1 form xa, xb. And that is nothing but the exterior derivative of the connection 1 form, hor xa, hor xb. Well, now they are vertical, so the horizontal part of them is 0. We know this, okay? But then this is a 2 form, a Lie algebra value 2 form, so it's bilinear. If one of the entries is 0, and here there are even 2, then the whole thing is 0. So in this case of both vector fields being vertical, the left-hand side vanishes. So we better find that the right-hand side vanishes as well. So what's the right-hand side? Plugging in these vector fields, we have d omega of xa, xb, plus omega, wedge omega, so double wedge omega of xa, xb. So what is this? Well, remember the definition of the exterior derivative of a whatever valued 1 form, that is xa acts on omega evaluated on the second entry minus the second entry acts on the 1 form evaluated on the first entry. Well, that's not all. For covariance, we also need that there is a minus the omega acts on the commutator of the two. And here this is the differential geometric commutator on the principal bundle. And then there's this extra term plus omega double wedge omega. But you see the double wedge was this guy up there. It's the Lie algebra bracket. This is the differential geometric bracket. But this is the Lie algebra bracket of omega xa, comma omega xb. That's right, huh? Okay, good. So how does this evaluate? Well, what is the omega of such a vertical vector field? Well, it just yields the Lie algebra element B that produced it. That's a property of omega being a connection 1 form. Here it yields the A. Here we mentioned this. This is the induced vector field, namely the one induced by x up a b with the Lie bracket, because this map is a Lie algebra homomorphism, this x up A, sends a Lie algebra element to a Lie algebra element, but the first Lie algebra it comes from is the Lie algebra of the group, and the other one is the Lie algebra of all the vector fields. And so so this A sent to XA is a Lie algebra homomorphism, and so it goes from the Lie algebra of the group to the Lie algebra of all vector fields gamma of TP. Now this is this map here. I don't know how to, well, that's the map. Okay, so this is a Lie algebra homomorphism. This fact plays into here, that, well, into this equal sign. Okay. All right. So how does that evaluate? Well, the omega of an x up something is again simply that bracket. And here, of course, again, the omega of the x up something is just the A, and that's just the B. And then we see in total, B is always the same B. It doesn't change. The XA acts on there. This all vanishes, vanishes, vanishes. This kills this, and there's a 0. Okay? So the left-hand side is 0, and the right-hand side is 0 in this case of both vector fields being vertical. Now what about the case B, that the vector fields are both horizontal, and then the case C will be that one is vertical and one is horizontal. So now let's assume x, y are both horizontal vector fields. Then again we have the left-hand side. Omega of x and y is the capital D omega of x and y, and that is simply the little d omega of horizontal part of x, horizontal part of y. But of course this horizontal projection has no further effect because x and y already are horizontal. So in this case it's simply the standard exterior derivative. Now the right-hand side starts precisely like that. It starts with d omega of x comma y, and here we're not going to use the definition of the d omega because we already have the term that we want. We just have to check whether the additional term vanishes, so that's the omega double wedge. So this double wedge is supposed to remind you of the double bracket, right? So that's why I have the double wedge. Suppose the same type here. Of x and y, okay, and so what is this? This is the omega of xx plus, so that's the Lie bracket of omega of x and omega of y, but now they're both horizontal, and in that case we know the omega acting on a horizontal vector field is of course 0. And that's a bilinear bracket, hence the entire bracket is 0. And indeed, the right-hand side is simply also the exterior derivative. So case B is also under control. And now we have the case C, that one of the vector fields is horizontal, the other one is vertical. It doesn't matter which, because on both sides we have antisymmetric expressions. So if we choose, in each case, the other one to be horizontal or vertical, then we'll get the same result with a minus sign, but on both sides, so it's the same again. Okay? So let's assume that without loss of generality, and that I just argued that it's without loss of generality, assume that x, say, is horizontal and y is vertical, hence it can be written as the induced vector field XA with respect to some Lie algebra element XA. Last time we evaluate the left-hand side. That's the omega of the x and the y, which is this here. And this is the d omega. You know it's the little d omega of the horizontal part of x and of the horizontal part of XA. But the horizontal part of a vertical vector field is 0. That suffices to annihilate the entire 2 form here, because it's of course bilinear, so the left-hand side is 0. And now the right-hand side is d omega of x comma xb. And yes, I think in this case we again have to expand this. And then there is a plus omega wedge omega of x and x a here. Okay. Okay, so I think we have to again write down the whole thing. Yeah, let's do that. Okay, so it's x acting on omega on XA minus XA acting on omega on x minus omega acting on the commutator, yes, on the commutator of x with XA, differential geometric commutator, plus the Lie algebra commutator of omega of the horizontal vector field and omega of the vertical vector field. Okay. So the omega acting on this one just yields the Lie algebra element A, on which x, of course, acts as a constant because it's a scale. Well, it's a Lie algebra valued constant function. Okay, so it's annihilated, that goes out, minus. So omega of a horizontal vector field is, of course, 0, also here. Now, the crucial point is here, you have a horizontal field together with a vertical field. We'll have to think about this. So let's just keep this here, x comma xa. And then back here, you have the omega of a horizontal field, and you know that that is 0. So I just don't need to, well, let's write it out for completeness, but it's clear that this guy goes, and this guy goes. So this must go. How could this go? Well, it's a fact that the commutator of a horizontal vector field with a vertical vector field is again horizontal. So this is again horizontal. Maybe put a little exercise like that on the problem sheet. And so it's annihilated by the omega. And so in total, you get 0. And the whole thing is proven. Okay, so you see, this is what I meant by the exterior covariant derivative is defined as the using this Hoare projection. Okay, but if you really want to calculate with it, the Hoare is difficult to calculate with. Well, you can evaluate it by plugging in corresponding vector fields, but it's better to have an expression like this. And so the proof relates the two. Good. Any questions? So again, I emphasize, as much as the connection 1 form is a 1 form, a Lie algebra valued 1 form on the principal bundle, on the total space of the principal bundle, as much as the curvature, as we define it here, a Lie algebra valued 2 form on the total space of the principal bundle. So probably the cases where you've heard of curvature so far in physics was always a 2 form or something of the type on the base manifold, okay, like the Riemann tensor or so. And we need to relate the notions. That's what we're going to do now. Okay, so we would now like to relate this to objects on the base space. So how do these definitions relate to objects on the base space. So we have here our principal G bundle on which there sits a connection 1 form, and now we have there sitting as well a curvature 2 form. Lie algebra valued 1 form, Lie algebra valued 2 form, both defined up here. And of course, we do this as always. We provide some section sigma from the base space up there. If there exists such a global section, the bundle must be trivial. Hence, we will generally restrict attention to a local section over some subset U of the base space. Okay? And one example, for instance, is in the frame bundle. You could choose down here a chart. So together with this U, you also choose a chart map. And then the section would be just attaching to each point in the base manifold by the chart, by the coordinates, induced frame at the point. That would be a very natural choice for a section, say, in the frame bundle, which is what you usually look at in differential geometry. Just to, again, remind you that there may be natural choices for what section you choose, but in fact you could choose any. Even if there's a natural choice, that doesn't compel you to make the natural choice. It's just, it shows you how this would play out in practice. So we need to choose a section, sigma. And then, of course, you remember what is the pullback of the connection 1 form under this section. How did we call that guy? The pullback of the connection 1 form? Locally is the... Bitte? Pardon me? It's Young-Mills field, exactly. And that induces a Young-Mills field and maybe this, we could call this gamma. That would remind us of the differential geometry case, or we could call it A. That would remind us of the gauge theory case in particle physics. But in any case, these are now Lie algebra valued 1 forms on, so Lie algebra valued 1 forms, but now on the base space. Okay? Well, that was the whole point of the Young-Mills field. And of course, I can do the same thing. So these are defined as, on the right-hand side, as the pullback of the curve of the connection, one form. But it also induces a new notion, which I introduce now, and that's a Young-Mills field strength. So a field is something different than a field strength. So strictly speaking, in electromagnetism, the electric field and the magnetic field together, which is the Faraday tensor F, is not the electromagnetic field, it's the electromagnetic field strength. And if anything is the electromagnetic field, then it's that what's called the gauge potential in physics. It's the A. The A is the field, and the capital A in electrodynamics is the field, and F is the field strength. So these are not synonymous, right? And the Young-Mills field strength is defined as the pullback of, you guess it, it's the pullback of the curvature. So under the same section, we may, of course, also pull back this 2 form, this Lie algebra valued 2 form, so that it lives down there. And that's then this guy. Okay? And that very often in differential geometry carries the name Riem for Riemann. And in gauge field theory, wherever, it very often carries the name F, like for instance in electrodynamics. Okay? Where do these guys live? Well, they all live in the space of two forms on the base manifold, but they're still Lie algebra valued. If the Lie algebra is abelian, like for instance U1, then you have an abelian F, an abelian field strength, okay? Or here an abelian field, right? That's electrodynamics. If this is a non-abelian, so non-commutative Lie algebra, then this is a non-abelian, this we would call a non-abelian gauge field, and so on, okay? Now, in differential geometry, the algebra we have here is GL. If there's no further structure on the manifold, we have GL dim M. That's not abelian. Well, they don't commute. Hence, the Riemann curvature on the base manifold is analogous to the non-abelian field strength in non-abelian gauge theories. It's just exactly the same thing. They're both, it's just, so this triple equal sign just means these are different names we choose in different areas of physics for exactly the same thing, namely the pullback of the connection 1 form as the Young-Mills field and the pullback of the curvature down to the base manifold. These are the objects that appear in physics, because in physics we like to talk locally, because that is where we do our experiments, where we deduce our formulae, and so on, okay? But if you think of this, and then you, in a sense, like to forget the principal bundle that sits over it. But really, the full structural idea you get up here. And you know that this guy transforms in an ugly way, right? There's this extra term of the gamma, if the gamma transforms, or the extra term here, right, under gauge transformations. This guy transforms better, okay? This you also know. You know, Riem, we say, is again a tensor, whereas on the base manifold, whereas this is not a tensor, right? So, but this trouble of the field not being tensorial, but the field strength again is this difference you only have down here at the base manifold level. That problem you don't have up here. Lie algebra valued 1 form, Lie algebra valued 2 form. So it's the artifact of pushing this down that produces the complicated transformation behavior here. It's the price you pay to make it local. Okay. And so now, after you did that, you of course observe the following. We had on the principal bundle, on P, we have this 2 form that is this exterior derivative of the Lie algebra valued 1 form plus the double wedge here. Okay? Now, if you push this down, so say we really look at the pullback of this field strength, of the curvature to the field strength, okay? Then, of course, this is the pullback of the right-hand side. Okay? But now, the pullback is, of course, linear. That means it distributes over this plus. Okay? But you will now also see that it also distributes over this wedge. So what you get in total, you get that, for instance, in differential geometry, the field strength, that's this guy, is the d gamma minus gamma wedge gamma. And if you think of the formulae, you know this also antisymmetrizes. This is simply the d gamma minus d gamma plus gamma gamma minus gamma gamma formula that you know. Because this is matrix valued, because we're over GL, so there's just this way they talk to each other, okay? And this formula you know, with the appropriate indices plugged in. And what is it? Riem is, of course, a 2 form, because it's a 2 form on here, because it's a 2 form up there. You pull it down by the pullback. That's a 2 form where these are tangent space indices, and because it's a 2 form, it's antisymmetric. It's a 2 form character of the Riem. But Riem also is Lie algebra valued, but the Lie algebra is a matrix algebra, so you have an up I and a down J. And without further structure, you do not know how to pull this guy down, much less do you know that they're antisymmetric or not. If you had a metric, you could pull this guy down, because this is the same range as these guys are. But more importantly, if you have a metric in the frame bundle, you can restrict the frame bundle from the GL frames to orthogonal frames, ON. But what is the property of the Lie algebra elements of an orthogonal group, the matrix elements of the Lie algebra of an orthogonal group? They are, they're antisymmetric, right? You saw this before, right? They're antisymmetric. I mean, the generators of the rotation group, for instance, they're antisymmetric. And that precisely is the antisymmetry of the first two here. So if you heard this in differential geometry, say in general relativity, that if the Riemann tensor comes from a covariant derivative that's metric compatible, blah, 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 then and only then is it antisymmetric in the first pair of indices as well. This has to do with the metric, but now we understand it as a property of the matrices representing the Lie algebra of GL, not of GL, the Lie algebra of O, the orthogonal group. Okay? And so you see these indices are really, it's only in the frame bundle that they have this structure, that they run over the same range here. So these 4 indices of the Riemann tensor, this up and this down index belong together, and the last 2 belong together. Okay? So we see it's a big coincidence what you have in the standard case, right? Okay, so this is this thing, but precisely the same, because gamma is A and Riem is F, precisely the same you have that the field strength in non-abelian gauge theory, but this is a non-abelian gauge theory, right, is dA plus A wedge A. Okay? And so these are the standard formulae so here we had a matrix group, so we can one matrix to the other minus the other to the one. This really becomes a commutator, this double bracket on the matrices, using the composition on the matrices or the matrix multiplication. Here, this is mostly written as del A minus del A, so del mu, A nu, and this guy back here now, the Lie algebra here is needn't necessarily be given by a matrix group, although mostly it is, but we could, for instance, also, if we label the Lie algebra indices now by a capital M and N, then we can write this as M N, and we put this wedge in between for the one form aspect, and the result is R valued, R valued, R valued, and this is then the R value. So this is the kind of stuff you see in non-abelian gauge theory as an expression, but it's precisely the same stuff, and here these guys simply encode the double Lie bracket, whatever it is. And mostly you can also write this as in matrix form with a commutator. Okay? But it's precisely the same. So all I want to show you is that these various formulae, this formula and this formula, are precisely the same. They're the pulled back versions of the connection 1 form and the curvature 2 form. Okay, and the idea that actually here the in differential geometry these guys here are just the pullbacks from up here, and that actually this differential geometry bit is as much a field strength of a one form and so on. This goes into ideas of how to canonically quantize gravity, right? So those of you who took the course on canonical quantum gravity, you know that that's the starting point there. Okay, questions so far? Good. So then there's an important identity we bring in the form of a theorem. That's the so-called Bianchi identity. And it's the Bianchi identity for curvature. And it's as simple as it can be. You take the covariant exterior derivative of curvature, and the result is 0. However, I should issue a warning. So first of all, I remind you that the omega itself is the covariant exterior derivative of the connection 1 form. So you say, oh, it's d squared on omega. Of course, it's 0. Well, that is not the case. So that's the warning sign. So while this is true, there is this caveat that in general, the d2 is not 0. Right? So the covariant exterior derivative squared is not 0 on everything, but it is 0 on the curvature. So the proof is not that simple. Okay? But it's not that difficult either, and it goes to the problem sheet. Okay, that's the Bianchi identity here. Okay, so now after the discussion of curvature, we come to the discussion of torsion. And as advertised in the beginning, again, the setting is a principal bundle, and it's also a principal bundle equipped with a connection. So the torsion is definitely a property of a connection, in our case a connection 1 form, but, and that's the important thing, it's not a property of a connection alone, it's the property of a connection and an extra structure which we call theta. So torsion requires these two. And what is this theta definition? If we have this situation of a principal bundle, then a V-valued one form theta, so that's our theta, on the total space of the principal bundle is called a solder form, and sometimes called soldering form, which is grammatically more correct. It's called a solder form if. So, okay, so, well, the 0th condition I already wrote down, that is that the theta is a one form, so this is of course not the curvature, this is just the space of one forms. So one form on P, and it is V valued. Well, what is V? V is a linear representation space of the group G, defining the principal G bundle, where V is a linear representation space of G. And I now add something which actually will follow from the last assumption, but why not make it explicit here? The dimension of V is not arbitrary. D must have the same dimension as the base space. So this is an important restriction. Not any vector space. Well, V is, of course, a vector space. A linear representation is a vector space. It must have the same dimension as the base manifold. Okay? So then this form theta is horizontal. That's just a statement that for every vector field on the total space, theta evaluated on the vertical part, yes, theta evaluated on the vertical part of the vector field vanishes. So sometimes one calls this a vertical one form on the total space. The third condition is and you see this is in stark contrast to the connection one form. So they're both one forms on the total space. This is Lie algebra valued, but this is linear representation space valued of this Lie algebra, different destination, okay? This one vanishes on the horizontal vector fields and doesn't vanish on the vertical ones, on the non-zero vertical vector fields. This one vanishes exactly on the vertical vector fields. Okay, so this is, I'm tempted to write here, unlike the connection one form omega. Now the third condition is like the connection one form omega, namely that if we consider the pullback of our soldering form theta, then the result will of course be again a one form on the bundle, because you see this goes from the bundle to the bundle. But it will be again V valued. Okay, I should tell you what this condition is about. This condition is, of course, supposed to be the G equivariance condition. Is supposed to ensure that if you move the solder form along the fiber, that is just that the solder form at one point is given by the solder form at another point, right? So there's a compatibility condition. And the last condition is, and that's one that will actually enforce this dim V equals dim M, is that the tangent bundle of the base manifold is supposed to be isomorphic to the associated bundle associated to this principal bundle with typical fiber V. And that makes sense because the G is supposed to act on the V anyway. That's a linear representation space. So this linear representation, of course, is the idea that I also use down there. So maybe this is the solution, really, that you have a linear, well, fixing a G, you have a linear map from V to V. Okay? That's this linear representation space, and so this operator here, this linear action of G on V should appear here. So that's, I guess this must be right. Okay. And they're supposed to be the same. Well, they could be the same as sets, as manifolds, as bundles. Well, they're in fact the same as associated bundles. Remember, there was a difference between a bundle map and an associated bundle map. An associated bundle map always comes from an underlying principal bundle map, right? And here, in this case, it's a principal bundle automorphism, and this is supposed to generate here an associate bundle isomorphism, and that is this fourth condition, from which it automatically follows that the dim V must be the dim M, but why not say this explicitly? Okay. So the idea behind this definition, the idea is to provide by the soldering form, so the soldering form or solder form is introduced to provide an identification of this chosen vector space V with each tangent space of M. Okay, that's the one and only idea behind this abstract definition. And the key example, or the obvious example, is to choose the principal bundle, total space, to be the frame bundle, where at every point over a smooth manifold in the fiber are all the frames that could sit there, all the tangent vector bases. And then we define a particular theta, in this case, as follows. It's a one form, so it takes a vector field on P, 2, and now I make a particular choice to R dim M. Well, R dim M here is to be identified with our V. This is clearly a dim M dimensional vector space. Okay. And how do I define it? Well, this is a one form, so I can define it at every point of the frame bundle. So, but the point of the frame bundle is just a frame at a point. So let's call a frame at a point, let's call this E, right? And then it acts on a vector field. And here we define it as, as the inverse of a map U, which is also defined for each E, for each frame. I'll say in a second how. After the push forward under the projection map of the bundle applied to X. Now I need to tell you what the U is, where the UE takes you from R dim M to the tangent space at the base point of the frame, so where the frame is attached. E is a frame. Frame is attached of the base manifold. How? Well, R dim M is just a dim M-fold Cartesian product, and this is supposed to be a linear map. And a linear map is given once I prescribe it on an arbitrary basis. So I choose on this Cartesian product, I choose the basis where this is the ith entry. Right? So if I have all these guys, I get this. And I map this to the E sub I, which is the ith vector of the frame. I have chosen a frame at a point, and I take the ith vector of the frame is assigned to this element in R dim M. Now, but here it's not the UE, it's the inverse of the UE. So here there's a little cloud. Well, it's clear that this is canonically there, right? If I have a frame, I can write this down. So I didn't introduce any extra structure. What we're doing here, if this is invertible, I'll show you in a second how. What we're defining here is a solder form on the frame bundle, but it's canonically defined. And hence, normally you don't even think of that there is such a structure. Okay? And hence one usually thinks, well, you can immediately write down the torsion of a connection well, the torsion comes in a second. You can immediately write down the Schuller form of the torsion of a connection, which is going to be defined in terms of the Schuller form. But in fact, this goes in between. And now the question is, what is this inverse? Well, you know this inverse. If this is a frame, E, then so E is a frame, a basis of the tangent space at some point. Then you know that you can look at a coframe, which is automatic. Well, okay, let's call it epsilon. You know, if you have a frame, then by duality you can define a coframe without extra structure. Okay, and in fact, you'll see that the UE inverse that is being used here is then, of course, a map from T, well, some pi of EM to RD. Well, what is that? Well, it takes an arbitrary vector here. Well, X is our vector on the principal bundle total space. This is supposed now to be a vector down there. Let's call it Z. Okay, so Z is a tangent vector to M, whereas X is a tangent vector to P. It takes a Z and it maps it to, you have a frame already chosen. You take the coframe of Z, and this will produce epsilon 1, epsilon 2, epsilon 3 will produce an element in RD. It's the components of these vectors. So what do you do? The Schuller form of a tangent vector to the total space. What do? You take the tangent vector to the total space and you push it down to the base manifold. So it's a tangent vector of the base manifold. And then you take its components. Of course, this is the collection of components. So the Schuller form in this case is just assigning components to it, but in order to assign components at a point, you need a basis. Well, this is why this guy at every point of this bundle is a basis. So it's defined. Okay? It's all quite trivial. Okay, so this is the Schuller form in this case, and that's the canonical Schuller form on the frame bundle. So now that we have an example for a Schuller form in this case, in other cases you might provide it by extra structure. You can make the following definition. So if P down to M pi is a principal G bundle, and omega is a connection 1 form, and theta is a Schuller form, again on the total space P, then the torsion capital theta, small theta, capital theta, is the exterior covariant derivative of the Schuller form. I could have called this T like torsion, but the T is reserved for the torsion once you push it down to the base space, but this is again up there on the principal bundle. Hence, we better also use, like for the curvature, we have the capital omega, here we have the capital theta. Okay? Then the torsion is defined as such, and what is it? Well, this is a 1 form, so the exterior covariant derivative makes this a 2 form. Makes this a 2 form where on the total space, and how is it valued? It's V valued. V being the representation space, linear representation space of dimension dim m of the group. Okay? So this is the torsion 2 form on P. And again, in this D is the horizontal projection in there. one can immediately show that the capital theta, the torsion, is the d theta plus the omega wedge the theta. Of course, the omega sits in here. So you see now the curvature was defined entirely in terms of the connection, but the torsion is defined in terms of the connection and the solder form. If you look at the frame bundle, which you often do in differential geometry, you can actually essentially identify the solder form with the co-frame. That you have to push this down first is because you anyway know, okay, I take this push down. So very often, so in general relativity, if you use the frame formalism, you would just say the thetas here, they have one index up. I would say there's the v, the index of the v space, but there's nothing but the number of the covector. Okay. So one could write this d epsilon plus omega wedge epsilon with a slight abuse of notation because you forget the push down, the push forward along the projection here, by which you have to take something down because really strictly speaking here, or strictly, it's just a fact, you're still on the total space. And in the formulae in general relativity, you very often think already of the push-down version. Then you write here the t, and it's again by the sigma pullback, you push this all down to the base space. And that's why then the theta becomes the epsilon. Okay? But still being up there, it's this formula. Now, we have here a similar problem. And this is Lie algebra valued. This is V valued. But the result is supposed to be V valued. So how do we get rid of this Lie algebra valued bit? Well, again, this is tradition, but in fact here, well, now the notation, you just have on one half, you have the double, a half double wedge. But of course, I need to declare what it means. And well, it's just the idea that you take the wedge as far as the one form character on P is concerned, but otherwise you let this Lie algebra element act on the theta because it can, because the V is a representation space of the group, but then also the Lie algebra can act on it, and that is what you do. At the end of the day, you have, therefore, that the theta has one I index if you have a matrix group. You have a matrix group, like GL, for instance, then you have a matrix algebra. And so far, Lie algebra valued has two indices because it needs to eat an element of the space it acts on, it needs to spit one out. But this one is only V valued, it has only one index. So this is the d theta with one index. Yeah, that's V valued. And now this guy here is Lie algebra valued IK. Then it is a one form for every combination IK. This can be as a one form wedged with the K, theta K, which is now for a fixed K only a one form. And then you see what I mean by this application. This just acts on here linearly. Okay, and this is a formula one then knows. Okay, and so finally we have a second Bianchi identity. Now, not a Bianchi identity for the curvature, but we have a Bianchi identity for the torsion as well. For the torsion, and that is again the capital T, D, sorry, the covariant exterior derivative acts on the capital theta, acts on the torsion, and the result is not 0, which is a particular example that the d squared is not 0, because the theta is just the d of the theta of the solder form. If capital D squared was 0, certainly we would get 0 here. We did for the curvature, but here we don't. In fact, we get the curvature 2 form wedged with the solder form. And again, it must be this application, so it must be, again, very strictly speaking, this guy here. So again, for a matrix group, d of the torsion being v valued is a 2 form, but a v valued 2 form, so it looks like this. Then you have the curvature 2 form here. Form? Hang on. It acts by ik wedge on the theta k. No, sorry, it's the 3 form. This is a 3 form. So the torsion is of course already a 2 form. So, of course. So this guy here is, of course, a v-valued 3 form on P, right? Yet another. So then you have a 3 form is a 3 form. I was concerned. Okay, so it's again v-valued because there you have the application. But this is a 2 form, this is a 1 form, this is a 3 form. And this is the Bianchi identity for the torsion. And that's also easy enough to prove it on the problem sheet. Okay, so again, point your attention to the image up there. In addition to the connection, you need a solder form in order to talk about the torsion, and that is why the torsion has only this one index up. And if you now want to again push it down to the base space by using some section sigma, you can of course define the T as the pullback of the torsion on the total space. And then of course this T is a 2 form on the base space, which is however of course still V valued. And that is the torsion you meet in general relativity if, for instance, you take the torsion on the tangent bundle with respect to some given connection, and then the T down there still has a V index up I, and the 2 indices down in the torsion that are antisymmetric are just the 2 form indices on the base space. So like in the Riemann tensor, we had Riem ij mu nu, so this is Ti mu nu, and in order to have this single I, even if you act with a matrix group, this must be a representation space there. And you now see why you need a representation space of the same dimension as the base space is. Okay. And so this will be the main application coming from the frame bundle, but there are other applications. So this soldering form is a more general concept, but at the end of the day, it will always produce this this isomorphism between this vector space here, dim R dim M, and the tangent space. And so in physics, we very often say that this is the internal space, right? This is the tangent space, and this is the internal space. And on here, we then establish an eta, which we get from here by pullback via this U map where we pull back the G, a Lorentzian metric, for instance, on each, so a Lorentzian inner product on each tangent space. We pull it back to an eta, and we do this in such a way such that this eta has the normal form 1, -1, -1, -1. Okay? Then we talk about the internal space and so on. And really, if you want to understand how this belongs together, this precisely is the task of the solder form. Okay? So this is the precise mathematical formulation of what is often only said in the frame formalism. And only that allows us to have torsion. Further questions? Okay, so this wraps up the mathematical part, and we continue on Tuesday with all the nice physics applications. Okay, thank you.